This figure shows the three proof techniques that are commonly used in matrix algebra. The three techniques are: first, direct proof; second, proof by contradiction; and third, proof by contrapositive. Direct proof. If you want to show that A implies B, or if A is true, then B is true, then using direct proof is when you want to assume that A is true, and then you want to show or prove that B is also true. Well, let's take a look at an example. Let A be an n by n matrix, and x and y are vectors in Rn. If you want to show that if A times x equals to A times y and x is not the same as y, then A, the matrix A, must be singular. Well, first, let's identify what is A and what is B. So in this situation, statement A is AX equals to AY, and x is not the same as y. And statement B is A must be singular. So using direct proof, I want to assume that A is true, which means I assume that A times x equals to A times y, and x is not the same as y. My goal is to show that A is singular. All right, so if we assume that A times x equals to A times y, we can move AY to the left to get A times x minus A times y equals to 0. And from this equation, we can factor the matrix A out to be A times x minus y equals to 0. At this point, we have a homogeneous system when A is a coefficient matrix and x minus y is a variable vector. So since we assume that A is not the same as y, then that means x minus y is not the same as 0. That means this system here, the system A times x minus y equals to 0, has a non-trivial solution. Okay, so by using the equivalent conditions for non-singularity, if a homogeneous system has a non-trivial solution, then the coefficient matrix A has to be singular. This is when I complete my proof. Proof by contradiction. Again, if you want to show A implies B, or if A is true, then B is also true. If you want to use the technique proof by contradictions, you want to assume that A is true and B is false. Then you're going to show that there is a contradiction to those assumptions. Okay. Again, you want to assume A is true and B is false, and try to find a contradiction to those assumptions. Well, let's look at an example. Let A and B are the two n by n matrices. You want to show that if A times B equals to A and B is not the same as the identity matrix, then A must be singular. Well, again, we want to identify what is A and what is B. In this case, A is A times B equals to A, and B is not the identity matrix, the statement A. And the statement B is A must be singular. So using proof by contradictions, I want to assume that A is true, which means assume that A times B equals to A, and B is not the identity matrix. Also, I assume that B is false. In this case, when statement B is A must be singular, so the false B has to be A is non-singular. Again, I assume that A times B equals to A, B is not the same as the identity matrix, and A is non-singular. And my goal is I need to come up with one contradiction. Okay, so keep going. Since A is non-singular, then there exists a unique inverse matrix, A inverse, right? And if I have A inverse, then I can multiply A inverse to both sides of this equations to get B equals to I. Once I multiply A inverse to both sides, the result is B equals to I, which is a contradiction because we assume that B is not the same as I. So once I show a contradiction, I'm done with my proof using contradiction. Proof by contrapositive. If you want to show that A implies B, or if A is true, then B is true using proof by contrapositive, you want to assume that the negation of B, then you want to show the negation of A. Let's look at an example. Let A be an n by n matrix. Let x and y be vectors in Rn. You want to show that if A times x equals to A times y, and x is not the same as y, then A must be singular. First, let's identify statement A and statement B. Well, statement A is x equals to ay, and x is not the same as y. And statement B is matrix A is singular. So look at the statement A, then we know that the negation of A is either AX is not the same as AY, or X is the same as Y. Also, the negation of B should be matrix A is non-singular. So using proof by contrapositive, we assume that A is non-singular. We assume the negation of B, and we want to show the negation of A. Okay, so if A is non-singular, then we can consider the system A times x minus y equals to 0. This is a homogeneous system, and since we know that A is non-singular, using the equivalent conditions for non-singularity, we know that this system here has only trivial solution, which is the solutions of 0. That implies A minus y has to be equals to 0, which means x equals to y. So once we show that if A is non-singular, x equals to y, which is the negation of the statement B, this is when we complete our proof by contrapositive.